Hello. Hello and welcome to the Studify Plus. Here we are starting our new chapter which is transient analysis. And in transient analysis, we will try to learn the transient analysis in two parts. The first part is the first order equation which is more popular for the exams, and for second we will go through the same circuit with the help of Laplace transform. So we are starting the transient. So let's understand first what is meaning of transient. Transient, and we are talking about which transient? A more meaningful transient, or also known as the DC transient. DC transient. So first we have to develop the understanding what is meaning of transient. Suppose I am having a resistor combination, a potential divider circuit. This is our potential divider circuit. Let's say we are having one pair of input and one pair of output. Let me call this value as R1. Let me call this value as 1 kilo ohm. Let me call this value as 1 kilo ohm. Correct? Let's try to understand the meaning of transient. And we are saying that this voltage is, let's say, V1. V1, any voltage you can apply at this point. And I am considering this terminal as V output terminal, and I am calculate the open load voltage across it. This is V out. Correct. This is so this circuit is known as potential divider circuit, or you can say this is voltage divider circuit. You can call this circuit as a voltage divider circuit. This circuit is, I am calling this circuit as voltage divider circuit. So if I say I have one waveform like this, and let's say this waveform is changing from 0 volt to 1 volt, means let's say this waveform is abruptly changing, or let me say this waveform is abruptly changing. Let's say it is going from 0 volt to 1 volt, or 0 volt to 2 volt, and this is, let's say, 2 volt. This is 0 volt to 2 volt. Which time? Let's say it is changing at t equal to 0. Again, we know that this is one potential divider circuit, and what is the output of potential divider circuit? So you can say the output of potential divider circuit here, if I draw the output waveform, the output waveform will looks like this. Output waveform will looks like this. If I calculate the output means what? I am calculating the potential across this 1 kilo ohm resistance. I am calculating the potential across this 1 kilo ohm resistance. So here with respect to time, I want to measure V output. And what is my observation? Because what is my observation? Let me draw the output. So can I say the output of this circuit will be, if input is going from 0 to 2 volt, the output of the circuit will go from 0 volt to 1 volt, because this is one potential divider circuit, and in potential divider circuit the potential will equally divided into two parts. So what we can say, our observation, the moment you try to fix the input voltage, or if input is taking a jump from 0 volt to 2 volt, if input is taking a jump from 0 volt to 2 volt, at the same point of time you are having a jump of input voltage from 0 to 1 volt at output resistance. So there is no transient, its behavior is same, abrupt behavior. So what I can say, abrupt change in input, abrupt change in input results abrupt change in output. So there is nothing new, there is abrupt change. Because resistance is an instantaneous component, so abrupt change in input will result abrupt change in output. Abrupt change in output. So you are getting some difference, a different output. The output is somewhat linear linearity. Output is somewhat linear version of input, but the change in input and change in output is having same nature, means abrupt change. But what if instead of this resistor, let's say I am using one energy storing element. Let's say I am keeping my first element same and I am keep changing my second element. This is case 2. I am keeping my first element same and I am changing my second element. This is the second element. Again, we are using some random values to understand the concept of transient. Why we are using transient here? Let's say this is 1 kilo ohm and this is, let's say, 1 microfarad. Now again the situation is same. Again the situation is same. I am calling this input as my Vi. I am calling this output as V output. And let's say again we are having the same situation. And what is our situation? Let's say input is again varying from 0 volt to 2 volt. So if I say my input is going from 0 volt to 2 volt, this is the nature of input. At t equal to 0, my input is going from 0 volt to 2 volt. Let's say input is going from 0 volt to 2 volt. This is one step kind of signal. Step signal is whenever we want to present abrupt change with discontinuity, unit step is there. So at t equal to 0, what we are saying, we are going from 0 volt to 2 volt. This is the amount of voltage I am applying at input. This signal is my Vi input signal. Now suppose we want to analyze the output. So in comparison to previous case, we will understand how, but in comparison to previous case, the output is different now. What is the nature of output? I can say the nature of output now is different from previous one. What was our previous output? The previous output was this. The nature of previous output is this. But now the nature of output, and we will analyze how we can get this waveform. We will do the mathematical representation. That is one of the important aspect. But let's understand what is the meaning of transient. We can say that now our output will go like this. Why? This difference is known as transient. This is the response of instantaneous component when only resistance are in the circuit, and this is when energy storing element are in the circuit. when we are having energy storing element in the circuit, and this response is known as complete response. So you can divide this response into two parts. So there is a concept which is known as 3 time constant and 4 time constant, but we are not going to that theory. But what is our general, what you can understand, the time after which the output is almost constant is known as a steady state solution of the this response. This response is known as steady state response. We will learn what is time constant, and this response we known as transient response. Although the name of chapter is transient analysis, but we will try to write the complete response of the circuit. So you can divide the analysis into two parts. So whenever we are having energy storing element, the energy, how energy storing element will behave with the abrupt change is known as transient analysis. So what is definition? Definition is how what is definition of the transient? We can say the definition of transient is very simple. How energy storing element energy storing element react to abrupt change. How energy storing element react to abrupt change, and this story is known as transient. So we can define this transient analysis in two parts. The first one is transient, and another, after that we will have the steady state response. Fine. So what we can say, the total response of the circuit, total response, let's say this is a circuit, electrical circuit with energy storing element. This is circuit. This is one circuit, and what I am saying, let's say you are applying input here. Let's say this is our input voltage, and this terminal represents the output. So what I am saying, first terminal is representing input. I am writing it VI, and second terminal is representing output. I am calling this terminal as V out. Both are function of time, of course function of time, because we are learning, we are dealing with energy storing elements, so with respect to time. And this is a network. This is our network having L and C and R. It is very important to have the energy storing element, otherwise there is no need of transient analysis. So what we are saying, the Y of t, the solution or response of the network can be divided into two parts. Means whenever you apply input, there can be two types of output. First, when you just changing your input abruptly, that is the reaction to that abruptness is one thing, and steady state output is another thing. So can I say, whenever you are having energy storing element in the circuit, we can say The output of the circuit can be divided into two parts. Output of the circuit can be divided into two parts. The first part is known as V output as transient solution. Transient, what is the definition of transient? That diodes is in steady state, that is transient. And another solution is known as steady state solution. Another solution is known as steady state solution. Correct? Or you can say that it is divided into two parts because generally energy storing element will form a differential equation, and you are having two kinds of solution. The first one is complementary function and second part is particular integral, or you can say this is response because of initial condition, or very popular term we call this zero input response. What zero input response means? Response due to initial conditions, ZIR. And what we call this? We call this force response. We call this force response. I hope this is clear. Or let me draw it here. Let me write it here. We call this PI as forced response. We call this response as a forced response. So what we can say, V output of T when T is approaching to infinity. Steady state means what? A long time. Means for a capacitor, it may be in microsecond or seconds, but we call this a steady state. So V output of T when T approaching to infinity is known as V output of steady state output. So you can say the definition of transient is very simple. V output of T minus V output when T is approaching to infinity is known as V transient. So we while writing the general solution, we have to take care of both. We have to write the steady state response or zero input response, and we have to write the transient response also. So this is our agenda for the day. This is agenda for the to know about both, to know about transient, to know about the steady state, and first we have to understand how energy storing element will behave with the time, because the nature of resistor is instantaneous. Means if you are changing the input voltage, you can at the same moment you will, because electric field established at the speed of light, so at the same moment you can have the change in output voltage. But you are having two energy storing element, inductor and capacitor. The nature of this two energy storing element is time depending. It depends on the time. I hope this is clear. So transient analysis we will divide in two parts. Transient analysis we can divide into two parts. The first part is using time domain approach, or you can say using differential equation. We will try to write the solution. First we will analyze with the help of time domain approach. In time domain approach, what we will do, we will form some differential equations and we will write the solution of differential equation and solve them. We will write the solution. And solution of the differential equation is response of the circuit. Correct? What is second approach? The second approach I will use is known as Laplace transform approach. What is second approach? Because what is the basic definition of Laplace transform? The basic definition of Laplace transform is to convert a differential equation into algebraic equation, and it is easy to deal with algebra, but with some rules. Means you cannot answer something a response in the Laplace domain. You have to bring again it into the time domain. So when you are going into the Laplace, you have to come back in Laplace transform again. So Laplace transform approach Laplace transform approach requires the knowledge of inverse Laplace transform also. A little bit of a very simple means how to take partial fraction, how a minimum, a very basic inverse Laplace means what is the Laplace transform of 1 divided by s plus 2. If you are aware of this, then you can say it is e to the power minus 2t into u of t. Means this solution is valid only for t greater than 0. This type of some very easy Laplace transforms are required, or only at second order Laplace transform are required. So I can say the inverse Laplace transform required. Knowledge of inverse Laplace transform is required when we are using Laplace transform approach. And in differential equation approach, the first in time domain approach, we can divide, and we will see this Laplace transform in detail, because for the second order circuit it is quite easy approach. In differential equation approach, we have to solve the differential equation. This is the only difference. But in differential equation approach, I will divide our whole analysis into two parts. And what these two parts are? First, we will go for first order analysis. What is our first agenda? We will go for first order analysis. What is first order analysis? We will analyze RL circuit. We will analyze RC circuit. I hope everyone is aware of what is order of analysis. Means the highest differentiation available in the differential equation is 1. Then we will go for second order analysis. In which we will analyze RLC circuit. Correct? So we will use this for first order and second order circuit. So first order and second order circuit is very important. First order circuit is the most important. You are having most question from the first order circuit. So in differential equation, we will solve the same circuit from the differential equation approach, and another one is using Laplace approach. We will use both the approaches to solve all the questions. I hope this is clear. Yes. Okay. Let's go for the next. we are having some energy storing elements. Means what is the main reason of transient? The main reason of transient is what? Transient or switching is what? Main reason of transient or switching is what? Energy storing elements. And we are having two energy storing elements. So let's see how this two energy storing element behaves. So let's go for this. What is the behavior of energy storing element? So we are starting from here, our observation about energy storing elements. And we are analyzing which circuit. We are here, we will focus only on first order circuits. So here we are here to analyze energy storing element. Energy storing elements. And we are having two energy storing element. The first element is what? First element we are having is inductor. First element we are having is inductor. And let's say inductor is having current IT and the voltage across inductor is Vt. This is very important equation. All your concept governs from here. And this is, let's say, the inductor, and the value of inductor is L Henry. This is our first component, energy storing component. So as we know that V L of t, the voltage across inductor can be written as L dit divided by dt. The differentiation of current is known as multiplied by L Henry is known as voltage induced across inductor. This much of volt. Now what I am saying, if I am interested in writing the expression of IT, can I say you have to multiply this t other side? So can I say VL, what is VL of t? Induced voltage across inductor, VL of t into dt, and this is divided by L. I am bringing this here. If divided by L, and if I integrate this, what I can do? If I integrate this, I will get the value of IT. So you can say IT is having two value. This integration is having limit from minus infinite to t. So you can say, because every differential equation is this is one differential equation, and differential equation gives you solution for t greater than 0 and initial condition is the constant. So can I say the I of t, this is very important concept, can be written as minus infinite to 0 VL of t divided by L into dt plus 0 to t VL of t into dt. Correct? This is because you know that the solution of differential equation is only valid for t greater than or equal to 0. So can I say this is one constant, and what is value of this constant? The value of this constant is I0 minus. What I am saying, this is our initial condition. If we want to analyze this, what we are saying, I0 minus, I am naming it I0 minus, and I0 minus is what? Initial condition of the inductor. Initial condition. Or you can say this response is also known as zero input response. When there is no input in the system, then response of the system is zero input response. And another is what? 1 divided by L integration of VLT into dt. This is what? This is IT. So first thing you can say, if initial condition of the inductor is current, means what we want to say, that inductor will store the, I will give you lot of examples in favor, but what we can say, inductor stores the energy in form of magnetic field, and what is basic variable? Basic variable is current. So I can say that IT can be written as I of 0 minus plus 1 by L integral of 0 to t VLT of dt. Now what I am saying, let's say I am interested in the current at t0 plus. So what is current at t0 plus? I at 0 plus t0 plus is equivalent to I at t equal to 0 minus plus 1 by L integral of 0 to 0 plus. Do you know that integral of a same point is what? Integral of a point is 0, because 0 to 0 plus is what? This integral is 0. And very important rule, because you know that differential equation is valid for t greater than 0. So we will calculate the initial, means whenever we are forming a differential equation will always generates the constant, and this number of constant is always equivalent to the order of differential equation. So how you can calculate the constant of a differential equation? Constant of a differential equation can be calculated at t greater than 0 only. So this is our first observation. T current at inductor at 0 plus is equivalent to current in inductor at 0 minus. We will try to give the meaning of 0 plus and 0 minus, but this condition is very important. What we are saying, what here 0 plus is representing? 0 plus is representing when you just connected your supply to the inductor. Just after connecting, what is meaning of T0 plus? Current or you can say a very important point we can write here, current across inductor current across inductor do not change, current across inductor do not change abruptly. Current across inductor do not change abruptly, but voltage can change. There is no such relation for the voltage across inductor. So keep in mind, no rule for the second point. There is no rule for voltage across inductor. There is no rule for voltage across inductor. So keep this thing in mind. One more thing. This is the first rule we have to remember. This is our prime rule. We will use this rule again and again in solution of all the questions. We will use this again and again. We will use this very important point again. Means voltage current across inductor do not change abruptly. This is our rule, but there is no such rule for voltage across inductor. Now what I am saying, our equation for the inductor, let me write it again. Let's have some few more concept. If I am saying this is our inductor, this is our inductor, and we are saying that this value is VLT, the voltage across inductor, and this value is IT. Then what we want to say, and this value is L. So can I say the stored energy stored energy in inductor what is the value of stored energy in the inductor? So can I say the stored energy in the inductor is given by the stored energy in the inductor is given by the stored energy in the inductor is given by half L I square. Correct? This is the stored energy in the inductor. So can we say inductor stores the energy in form of current? Because it is only dependent on what? Current. Inductor stores the energy in form of current. If inductor stores the energy in form of current, then can I say, let's say there are two cases. There can be two cases. Either you are charging the inductor or you are discharging the inductor. Means in the circuit, inductor is discharging itself or charging. So can I say I am taking first condition. Case 1, when we are charging the inductor. Inductor is when inductor is charging. When you are charging the inductor, what I can say this can be the charging. What is the pattern of charging? The pattern of charging can be this. If I write only, we will discuss 3-4 waveform. Only this waveform you will observe in all first order circuit. So in all first order circuit, all waveforms are valid. So this is time, let's say, and let's say maximum you are charging the inductor. Means I am writing the waveform of current. This is I. So can I say your waveform can be charged like this? Yes or no? Only this type of you can have the solution nature of this waveform with the help of differential equation, solution of differential equation, but just assume that this kind of waveform we are having. So this is the point where the inductor is maximally charged. Maximum charging is here. If maximum charging is here, can I say what is the value of derivative dit divided by dt? As you know, this is the characteristics of the maxima, that the value of derivative is 0. So can I say what is the VL equal to L dit divided by dt? And where you will get the maximum charging, you will get maximum charging in a steady state. So can I say the voltage across inductor in steady state? What is we generally represent steady state by what? For a long time, if inductor is connected in some circuit, we will discuss it more detail. So in a steady state, or let me write, instead of time, let me write this value as a steady state value. Let's say we are interested in steady state value of inductor. So can I say the voltage across inductor in steady state is what? Steady state means for a long time. T equal to infinity, minus infinity may confuse you, but this will not confuse you. And what we can say, dit divided by dt is equivalent to 0. If this value is equivalent to 0, the voltage across it is also equivalent to 0. So what we can say, inductor behaves as a short circuit in the steady state. So what we can say, let's say this is your inductor. We are having one inductor. This is our inductor, correct? And let's say some source is connected to this inductor. Let me say some source is connected to this inductor. Let me say some source is connected to the inductor. Some source is connected to the inductor. Let me. Some source is connected to the inductor, and what we are saying, let's say there is a lot of time for a long duration it is connected to the inductor. Then what we can say, you can measure the stored current in the inductor by replacing it by short circuit. So what we can say, just this is your source and you want to calculate that how much current is flowing across inductor, then you can measure it by replacing it to the short circuit. Because how it will behave in a steady state. So what we are saying, let's say this point is t equal to 0. What we are saying, you will get this type of notation. Let's say this point is t equal to 0. T equal to 0 means at t equal to 0 moment I am connecting my inductor to the source. So what I am saying, if you want to measure the current at t equal to infinity means what? In a steady state. What this t equal to infinity is known as steady state. So you can say in a steady state, you can measure the current you are connected to the same source. So in a steady state, what we are saying, that voltage is equivalent to 0. VL of infinity is equivalent to 0. And this current is which current? VL of infinity is 0 means in steady state the voltage across inductor is 0, and this current can be IL of infinity can be measured by replacing it to the short circuit, correct? But t equal to 0 is we have to take care about the duration. So how to achieve the steady state? If you are starting from t equal to 0, t equal to infinite is the steady state. But let's say in some cases, because we are too much of in the analysis of switching. So if you are starting from t equal to minus infinity, You can say t equal to 0 is minus is also one steady state. So this is initial time and this is the final time, or you can say this is also steady state. So steady state analysis or steady state point is dependent on starting point. What is this? This is starting point. Starting point. So if you are starting from t equal to 0, you can say t equal to infinite means uh, if you are starting from here, t equal to infinite will be the steady state. Infinite is a very relative term because we talks in terms of time constant, and time constants are also given in the microseconds. But when you are starting from t equal to minus infinity, this is before and after switch condition. Minus infinity and plus infinity is before and after switching condition that we will analyze. But what is the main thing? Inductor behaves as a short circuit in the steady state. This is the point. So what we can say here, our conclusion is what? Inductor behave as short circuit in steady state. Inductor behaves as a short circuit in the steady state. I hope this is clear. Inductor will behave as a short circuit in the steady state. So this is the waveform for charging of the inductor. But steady state, this can be charged or this can be discharged. What is the case number 1 part 2? Again, let's analyze the case number 1 part 2. Because when you are having energy storing element, there can be two things. The first thing is what? The first thing, you can charge the component, or what is the second thing? You can discharge the component. Means suppose this is one inductor, let's say case 1 part 2. Here we are having case 1 and part 2. We will connect all the points. Suppose this inductor is, suppose I am having that inductor and this inductor is connected to the load. This is, let's say, charge inductor. Inductor is what? Charge inductor. It is having some initial value. Some initial value is given. Let's say that inductor is charged by how many ampere? Let's say 2 ampere. It is charged by 2 ampere. And here we are having one load. Correct? This is what? This is one load. I am calling it RL or any type of load. Correct? So how our inductor will behave with this? So what I am saying, and I am calling this voltage as VT and this current as IT. So what can be the possible waveforms? You will say that this inductor will discharge through the load. So I am calling that my inductor will discharge through the load. So I am calling this value as IT and this is T. And what is the possible nature of the waveform? The possible nature of the waveform is this. This is the outcome of some differential equation. And can I say this point is, again, this is the minimum current. This is the minimum current inside the inductor. Can I say here at minimum point the value of di divided by dt is again 0, because whether it is maxima or minima, the value of tangent is 0. If the value of tangent is 0, can I say VLT equal to L dit by dt. And in case of discharging also, in case of discharging of the inductor, this value is 0, and this value is 0 means VLT is 0, and VLT is 0 means what? Voltage is 0 means what? Short circuited. So what is our conclusion? Whether inductor is charging or inductor is discharging, in both the cases you can replace inductor by steady state in, you can replace your inductor in steady state in, you can replace your inductor by the short circuit in the steady state. So we don't care whether it is charging or not charging. The behavior of inductor in the steady state is always a short circuited one. I hope this is clear. So this statement is very important for us. The inductor behaves as a short circuit in steady state, and we don't care whether your short circuit point is, which point is short circuit. If you are starting t equal to 0, t equal to infinity is a short circuit. If you are starting t equal to minus infinity, then t equal to 0 minus is another short circuit. I will define this meaning of t equal to minus infinite and t equal to 0 minus and 0 plus. What what is the meaning of this variables t0 minus? What is meaning of t equal to infinity? We will define everything. So we have seen about two things about inductor. The first thing is what? The current across inductor do not change abruptly. Second point is what? The second point is there is no such rule for the voltage. The second point is what? Or the third point is what? Whether you are charging your inductor or the inductor is discharging, in both the cases, in steady state, you can replace your inductor by short circuit. These are the whole conclusion of our analysis of the inductor. This much of information is enough to approach any question. I hope this is clear. Is it okay? Okay. So let's go to the points. We have talked about inductor. Our next component is a very important component, that is known as capacitor. That component is known as capacitor. So let's talk about capacitor now. What is our next component? Capacitor. This is one capacitor. And we don't want to focus on the AC behavior, means we will discuss that in AC analysis. We have talked about it in AC analysis. Always remember, across a passive element, current always enter from the positive polarity. So this is the current. Let me call this current as IT. And this is the voltage across capacitor, that is VT. I am not writing it VCT or ICT, VT and IT. And what is basic rule? We know that current across inductor, capacitor is given by what? IT equal to C dVT divided by dt. This is the value of current across capacitor. This much of ampere or milliampere, whatever the unit you are having. Or I can say the voltage across inductor VT is given by what? The value of voltage across inductor is given by what? Just multiply IT by T dt. So IT into dt divided by C. IT into dt divided by C, and we are having differentiation here. So you can say this is one integral. And what is limit of this integral? Minus infinite to t. Always remember, your differential equation will provide you two types of solution. First is zero input response and another one is forced response. Now you can say the voltage across inductor can be divided into two categories. V of t can be written as minus infinite to 0, or always remember this is continuous function, so minus infinite to 0 minus, I will define what 0 minus, what is t. Every point is having special meaning. It divided by c into dt, or you can say this value is what, 0 to t it into dt divided by c. Correct? Can I say if this represents the voltage, Vt can be represented as, what is minus infinite to 0 minus? Minus infinite to 0 minus is again energy stored, or the voltage. We are calling this voltage as V minus, and this is Cf. In all physical components, the available components, the initial condition do not vary with the time. It happens only in mathematics, and where it is, we are having 1 by c 0 to t it dt. Now what we are saying, if we want to analyze this at t equal to 0 plus, this value is constant, v of t equal to 0 minus, and when you calculate integral from 0 to 0, this value is again equal to 0. So what we can say, across inductor, what we can say, across inductor, v0 minus equal to v0 plus. Always remember this. The voltage across capacitor do not change abruptly. What is the second concept we are having? The voltage across capacitor will not change abruptly. Very important concept. Voltage across capacitor do not change वोल्टेज अक्रॉस कैपेसिटर डू नॉट चेंज एब्रप्टली, कि किसी भी कैपेसिटर के अक्रॉस वोल्टेज जो है वो एब्रप्टली चेंज नहीं होगा. It happens with the time constant. We will talk about everything. So this is our first concept about capacitor. So we have seen the three concepts for the inductor, that it stores the energy in form of current. The first concept means in magnetic field. The second concept is the current across inductor do not change abruptly. Second concept. And third concept, in steady state. In steady state means when a component is connected in the circuit for longer duration. What we are saying, for in steady state, you can measure the stored current in the inductor by replacing the inductor by short circuit. That is very important point. Whether you are charging the inductor or inductor is being discharged, in both the cases, if steady state is there, steady state means for a long duration of time the component is connected in the circuit. So in the steady state you can replace your inductor by what? Short circuit. So in the same way we are doing it for the capacitor now. The another energy storing element we are having is the capacitor. And what we want to say about capacitor, across a capacitor the voltage do not change abruptly, means but there is no rule for current in the capacitor. So what we are saying, You can apply this concept to the voltage across capacitor, but there is no this statement is not valid for the current across voltage. No rule for current across current can vary abruptly across the capacitor. There is no rule for the capacitor. I hope this is clear. Now we want to know about more things. What is the behavior of capacitor when it is connected in the circuit for a longer duration of time? So let's talk about that. This is case number 2. What I am saying, let's say we are having one capacitor. What is this is one capacitor. The capacitance is C farad. This is the voltage applied across the capacitor, and this is IT. Now what I am saying, how capacitor stores the energy? Do you know that it stores the energy in form of electric field, but stored energy is half CV square. If stored energy is the half CV square, means capacitor will store the energy in form of voltage, or it accumulate the charge. And who will bring the charge? The current will bring the charge. So half CV square means store the energy. It stores the energy in form of voltage. Correct. It stores the energy in form of voltage. Now what I am saying, let's say it is storing the energy till the maximum point, and let's say it is charging and discharging. So let's say let capacitor is charging. Let's say capacitor is charging. Let's say capacitor is charging means, let's say capacitor is connected to some source via some network, also fine, but we are taking the extreme case that let's say directly it is connected to some source. Let's say you are having some source. This is one source, and let's say here we are having one capacitor, and the time is specified. When I am connecting this capacitor to the source, let's say I am connecting this source to the capacitor C. Let's say t equal to 0 is the time. Our reference time means whenever we are starting whenever I am connecting this capacitor to the circuit, I am calling this time is t equal to 0. Let's say this is connected to the circuit at t equal to 0. I want to know what is the behavior of this capacitor at t equal to infinity. Means I want to know its steady state behavior. How this will behaves in a steady state. Let's say this is the point where we have achieved the steady state. Always remember the time constant of the capacitor is 1 microsecond or 2 microsecond, and generally steady state is 4 times of time constant, so or 3 times of time constant is standard value, or 5 times of time constants. So this value is very less, but for theoretical reasons, for mathematical expression point of view, what we are saying, that we have connected our capacitor to the source at t equal to 0, and how our capacitor will behave in steady state. So can I say, if you want to calculate, if you want to know how your capacitor will behave in steady state, you can calculate it very easily. How you can calculate it? We can calculate it by a very simple thing, by the concept of minimum and maximum value. We can calculate it. Let's say this is capacitor, and we are calling the voltage across capacitor, this is again same source, and we are calling this voltage as V of infinity. V of infinity means a capacitor is connected in the circuit for long duration of time, and in that duration, how our capacitor is storing the energy. So can I say, capacitor stores the energy in form of voltage. So voltage will rise in the capacitor, yes or no? When suppose it is charging, so when it is charging, the voltage will rise in the, so what I am saying, this voltage is, this is the voltage waveform, this is V, this is I is a function of time, this is voltage across capacitor is a function of time, and this is the, let's say, maximum voltage it can store, or this is equivalent to the source voltage. Now what I am saying, I am saying that it will starts charging, and when it goes to the maximum value, you know the behavior of tangent at the maximum value. Can I say, at maximum value the tangent is equivalent to 0. Which tangent? This tangent, dv by dt, dv by dt tangent, this value is not I, this is t, because with respect to time, with respect to time, what we can say, with respect to time, the voltage is increasing inside the capacitor, means capacitor will accumulate the charge carrier, accumulation of the charge carrier is known as voltage. So voltage is increasing across the capacitor. If voltage is increasing across the capacitor, can I say at the maximum, at the maximum, this is, let's say, V maximum, and when it is reaches to the maximum value, the derivative of tangent is 0, and you know that I is given by LD C dV by dt. So I of infinity is also equivalent to 0. If I is infinity is also equivalent to 0, can I say current is 0 means what? Open circuited. Means current 0 means what? Current 0 can be replaced by what? Current 0 can be replaced by open circuit. So can I say, we will replace this voltage by open circuit. So in steady state, in steady state, how your circuit will behave? In steady state, your circuit will behave as open circuit. Behave as open circuit means the total voltage, the total potential of the circuit will appear across the capacitor, and now the potential difference between these 2 points is 0. That's why current is equivalent to 0. The reasoning of current, why current is equivalent to 0? Let's say you are having source as 2 volt, and now in steady state the voltage across capacitor is also 2 volt. If both are 2 volt, what will be the current? The current will be 0. So this is the first, let's capacitor is charging, this is the case. Let's say this is the first case when capacitor is charging. But we can calculate the second case when capacitor is discharging. What happens to the circuit when capacitor is discharging? And that is another case. I am taking the second case. Let capacitor is discharging. We are taking the second case when capacitor is discharging. And when capacitor is discharging, how we will represent it? Let's say we are having one capacitor. This is one capacitor we are having, and capacitor is having some initial voltage Vc0 minus, and Vc0 minus is, let's say, 5 volt. Now you are connecting this capacitor with a load. This is load, some load resistance is connected. Any kind of load is connected. Let's say this capacitor is connected to the load. So what is the initial value of the capacitor? So can I say the initial value of the capacitor is what? Initial value of the capacitor is 5 volt. And this 5 volt potential is available at t equal to 0. This 5 volt capacitor is available at t equal to 0. Now what we want to analyze? We want to analyze what is the behavior of this capacitor in the steady state. So let's say if we are starting from t equal to 0 second, 1 second or 2 second, any point of reference is fine. Even if you are starting from t equal to 0 second or 1 second or 2 second, t equal to infinity will be always the steady state. And what we are saying, in this duration your capacitor will discharge. In this duration the capacitor will discharge. This is the voltage across capacitor, and this is the time. I am calling this as a voltage across capacitor, and this is time. Let's say the capacitor is discharging. If capacitor is discharging, it will reach up to the minimum value. I am calling this value as V minimum. V minimum, and at minimum value, can I say the value of dV by dt is again 0, because this is the characteristics of minima. dV by dt is again equivalent to 0. If dV by dt equivalent to 0, you know that how we define the I is C dV by dt, and C dV by dt equal to 0 means again the current is 0, and current is 0 means open circuited. So you can say across a load in steady state, you can again replace your capacitor by what? Open circuit. Yes or no? The current will be 0. The current will flow only that duration. So again it is very clear whether you are charging your capacitor or whether you are discharging your capacitor. In steady state, the capacitor will behave as a open circuit. So what we can say, in steady state, very important point, in steady state capacitor will behave as open circuit. Whether you are charging the capacitor or discharging the capacitor, we don't care about this fact, but the capacitor will behave as an open circuit in the steady state. This is very important point. So we are having two energy storing element in the circuit, and we know what is the steady state behavior of this energy storing elements. But our question comes with the concept of switch. So we will apply a switch in between. There are two steady states. When you are starting from t equal to minus infinite, the zero is one is of the steady state, and when you are starting from t equal to 0, t equal to infinite is another steady state. So we will try to analyze our circuit for both the steady states, and we will use the concept of abrupt changing or not abrupt changing the voltage and current at when we are going from one state to another state. So it is concept now that the capacitor in the steady state will behave as an open circuit, and inductor behave as a short circuit in the steady state. These two are very important concept. So, and this statement is true in the both the cases when you are charging your inductor or when the inductor is discharging from the circuit, discharging through a load, or you are charging your inductor. In both the cases, this statement is true. So what is the conclusion of today's class? The conclusion of today's class is very simple, that transient can be analysis into two parts, the in two ways. The first is Laplace and second way is differential equation. uh, we are learning first case, which is very important to us, differential equation. And for learning differential equation, first we have to analyze our components. So we are having two energy storing elements. First is inductor, and about inductor we know that it stores the energy in form of current, the first thing. Second thing is the current across inductor do not change abruptly. What is third thing? The inductor behaves as a short circuit, means the voltage across inductor will be zero in steady state. That's why it will behave as a short circuit. What is another case? Another case is this nature is true whether you are charging your inductor or whether you are discharging your inductor. Both the cases it is true. Second, charging and discharging both the cases is true. Mithun, I will see your doubt. What is second case? The second case is for the capacitor. One thing about the capacitor, the voltage across capacitor do not change abruptly. The first thing we have to ask, we have to focus. Second thing is what? The second thing is voltage. Capacitor stores the voltage energy in form of voltage or in electric field. Third case, in a steady state, the capacitor's current will be zero. Why current will be zero? Because source will charge the capacitor. And in case of charging and in case of discharging, in both the cases, the voltage tangent will be zero. That's why we can say it will behave as a open circuit, because I equal to C dV by dt so it will behave as a open circuit. We will use these concepts to we will apply this concept in our analysis of transient. I hope this is clear. So we will solve few more questions, and we will solve all the variety of question in the coming session. In next session, we will see the concept of the time constant also. Thank you very much.